Red Bull fuels millions every day, but behind each can is a factory process so fast and intense, it runs like a machine on overdrive. From precision blending to high-speed filling and global distribution, every step is engineered to deliver the same energy-packed formula at a massive scale. In this documentary, we take you inside the factory to see how Red Bull is made, from raw ingredients to the iconic can that gives you wings. The production of Red Bull starts long before the filling lines come to life. It begins at the sourcing and logistics stage, where each raw material used in the drink is carefully specified, contracted, and verified to meet the company's global quality standards. Although the ingredient list appears relatively simple: water, sucrose, glucose, citric acid, carbon dioxide, caffeine, taurine, B vitamins, and flavorings, the level of control and traceability involved in acquiring each component is remarkably complex. We begin with the most abundant ingredient: water. Water makes up the vast majority of the product, and its quality is absolutely critical. Unlike municipal tap water used in smaller food and beverage operations, the water used in Red Bull production must conform to pharmaceutical-grade purity standards. This means it undergoes extensive filtration, mineral balancing, and microbiological testing before it ever reaches the mixing tanks. In most Red Bull factories, water is drawn from deep, protected aquifers or dedicated water sources that are tested daily. The water is pumped into on-site treatment plants where it first passes through coarse filtration to remove particulate matter like sand or debris. It is then passed through activated carbon filters to strip away chlorine, organic compounds, or any remaining trace contaminants that could affect taste or chemical stability. The next step is typically reverse osmosis, a membrane-based filtration system that removes dissolved solids at a molecular level. This process reduces the water to an ultra-clean base, free of minerals, microbes, or off flavors. Once the water is purified, it enters holding tanks constructed from polished stainless steel. These tanks are fitted with level sensors, CIP spray heads, and temperature regulation systems to maintain stability. Water is kept in motion using gentle agitators or circulation pumps to avoid stagnation and ensure readiness for blending. Meanwhile, the sugar content of Red Bull, derived from both sucrose and glucose, requires its own specialized preparation. Red Bull uses a combination of these two carbohydrates to create its sweet but not overly cloying flavor profile. These sugars are sourced from sugar beets and corn and arrive at the plant either in dry crystalline form or as concentrated syrups, depending on regional supply chains. In facilities that receive dry sugar, the ingredient is pneumatically conveyed from delivery trucks into sealed sugar silos. These silos are climate controlled to prevent moisture absorption and equipped with weight sensors to track inventory in real time. When ready for production, the sugar is transferred to large dissolving tanks where it is combined with hot, purified water and mixed using high shear agitators to create a uniform syrup. This syrup is passed through mesh filters to remove any undissolved particles, then sent to a holding tank where it is cooled and held under sterile conditions. For glucose syrup, the process is slightly different. Delivered in bulk liquid containers or tanker trucks, the syrup is pumped through heated, insulated lines to prevent crystallization during transfer. Inline flow meters and viscosity sensors are used to ensure consistency. Once in the storage tanks, the glucose syrup is sampled and tested for pH, sugar concentration, and microbial stability before being cleared for blending. Now comes taurine, one of the most distinctive and chemically sensitive ingredients in the formula. Taurine is an amino acid-like compound that plays a role in neurological development and cellular hydration. It is synthesized in pharmaceutical-grade chemical plants through a controlled reaction involving ethylene oxide and sodium bisulfite, resulting in a high-purity crystalline powder. Red Bull does not extract taurine from animal sources. It is entirely synthetically produced for purity and consistency. Taurine is delivered to the beverage plant in sealed drums or lined bags inside rigid totes. Upon arrival, each container is inspected and sampled. The contents are tested for purity using high-performance liquid chromatography and screened for heavy metals and microbial contamination. Once cleared, the powder is either stored in a dry room or moved directly to the batching area, where it is weighed with precision down to the gram using automated ingredient scales. Caffeine, another central functional ingredient, is handled with similar precision. Synthetic caffeine, which is chemically identical to naturally occurring caffeine, is the preferred form in most facilities due to its purity and consistency. It arrives in fine white powder form, packaged in airtight containers to prevent oxidation and contamination. Like taurine, caffeine is dosed in tightly controlled quantities. Too much, and the drink becomes bitter or risks regulatory violation. Too little, and the expected stimulant effect may be lost. B group vitamins, specifically niacin, pantothenic acid, vitamin B6, and vitamin B12, are delivered in stabilized powder form. These micronutrients are highly sensitive to heat, light, and oxygen, so they are packaged in light-blocking, nitrogen-flushed containers. They are stored in temperature-controlled rooms and only opened at the time of production. Dosing is managed using micro-feeding systems, capable of adding quantities in the milligram range with high accuracy. Citric acid, used to balance sweetness and enhance shelf life, is one of the more straightforward ingredients. It arrives in either crystalline or liquid form, depending on plant setup. Like the sugars, citric acid is dissolved or diluted in purified water, filtered, and then pumped into blending tanks using stainless steel sanitary piping. It is included not only for flavor, but also to regulate the final pH of the drink, which has an impact on microbial resistance and carbonation behavior. The final core ingredient, prepared before blending, is carbon dioxide. Although it's added at the end of the line during filling, CO2 must be stored on-site in large insulated tanks under high pressure. This gas is certified food grade and must meet stringent standards for purity and dryness. Impurities in the gas, such as hydrocarbons or sulfur compounds, can result in off flavors or affect carbonation stability. Inline purifiers and moisture traps ensure that the gas remains within specification as it travels to the carbonation units. At this stage, all the major ingredients have been separately received, prepared, filtered, and stored in secure holding tanks, each one monitored by a network of sensors and controlled through a centralized process control system. The factory is now ready to enter the next phase, the blending and batch formulation process, where the base liquid is built step by step from these prepared components under tightly monitored conditions. Inside the blending hall of a Red Bull manufacturing plant, massive stainless steel tanks, often tens of thousands of liters in capacity, stand ready to receive pre-prepared ingredients. Each of these tanks is built with industrial mixers at the base and along the walls, with baffles designed to eliminate dead zones and ensure even distribution of all ingredients once mixing begins. These aren't just glorified vats, they're engineered systems with flow sensors, agitation controllers, and automated dosing inlets. Blending starts with the base, purified water. A calibrated volume is pumped into the blending tank. From here, the sweetener solution is added. By this point, the sugar and glucose have been dissolved into a consistent syrup in separate vessels and passed through fine mesh filters to remove any undissolved particles. They're now gravity-fed or pumped into the main tank through metered valves, which record the exact volume added in real time. At this stage, the solution is still colorless, with a mild sweetness and a viscosity slightly thicker than water. Stirring begins slowly, just enough to encourage circulation without aerating the mixture prematurely. Once the sweet base is established, the functional ingredients are added in a very specific sequence. This isn't just for convenience, it's chemical. Caffeine, taurine, and vitamins each behave differently depending on the pH, temperature, and concentration of the liquid they're introduced into. To ensure even dissolution, caffeine is dosed in carefully, often pre-blended into a neutral, aqueous solution to avoid clumping. Taurine, being more soluble, can be introduced directly, but at a steady rate to avoid localized saturation. The temperature of the blend is strictly controlled during this entire process, typically kept between 10 degrees C and 15 degrees. Keeping the temperature low helps prevent degradation of the heat-sensitive components, especially the B vitamins, and also limits the risk of microbial growth. Inline cooling jackets on the tank walls help regulate this, while digital sensors constantly send data to the factory's main control panel. After the active ingredients are in and fully dissolved, the next step is homogenization. While Red Bull is a clear drink and doesn't have oil-based elements like some emulsified beverages, this process is still used to ensure complete molecular distribution. A high-speed rotor-stator mixer is activated to subject the liquid to intense shear forces, ensuring that no microclumps or undissolved pockets remain. Think of this as the industrial version of making sure your recipe has no lumps, but at a scale where a few unblended grams could ruin an entire batch worth millions of servings. Once homogenized, the blend is passed through a fine filter system, often absolute rated filters that remove particles down to the sub-micron level. This is the final polish of the beverage, ensuring not just clarity and texture, but also eliminating any particulate matter that could interfere with carbonation or filling equipment. Now, the finished liquid base is sent to a storage tank, often referred to as the balance tank, which feeds the carbonation system. At this stage, the liquid is still uncarbonated. Carbonation must be done with surgical accuracy, both in timing and in gas levels. Too early, and carbon dioxide can escape during filling. Too late, and the drink will feel flat. Before carbonation, the balance tank contents are degassed using a gentle vacuum system to remove any dissolved air from the blend, air that could interfere with carbonation or introduce unwanted oxygen into the final product, leading to flavor instability over time. Carbonation is introduced through a high-precision saturator. This device uses temperature, pressure, and turbulence to force carbon dioxide into the liquid. The lower the temperature, the more CO2 the liquid can absorb, so the beverage is chilled further just before entering the saturator. Inside the unit, the liquid flows in a turbulent spiral while pressurized CO2 is injected. Sensors monitor saturation levels down to fractions of a gram per liter, and the flow is fine-tuned via automated valves. Once carbonated, the beverage is immediately transferred to the filler line. No storage, no delay. At this point, any agitation or exposure to heat could cause gas to escape, so the tubing, valves, and tanks are all designed to reduce turbulence. The product is now ready to be introduced into cans. Filling lines in a Red Bull factory are among the fastest and most technologically advanced in the beverage industry. The cans themselves arrive at the plant in stacks of blank aluminum cylinders, unprinted or pre-printed depending on the factory setup. These cans are depalletized automatically and conveyed upright to the rinser station. Here, they're inverted and sprayed internally with deionized water or sterile air to remove dust or particulates. From the rinser, the cans travel on a conveyor to the filler. This machine uses a gravity or counter-pressure system to fill each can precisely while preserving carbonation. The can enters the fill station, is sealed around the top rim with a flexible gasket, and then filled from the bottom up with cold, pressurized beverage. Fill levels are controlled within a margin of plus 0.5 grams to ensure legal compliance with net content regulations and consistent customer experience. Immediately after filling, the can passes to the seamer, where a pre-formed aluminum lid, known as the end, is dropped onto the top and crimped into place. This creates an airtight seal. Seamers are some of the most mechanically intricate machines in the entire facility, operating at speeds of over 1,000 cans per minute while performing multiple precision operations in less than a second per unit. After sealing, the cans are rinsed externally to remove any spillage and pass through a drying tunnel. They then enter the inspection phase. Here, cameras and sensors verify the seal integrity, check fill levels using X-ray or gamma ray detection, and inspect for dents, deformations, or labeling defects. Any can that fails inspection is automatically ejected from the line. Cans that pass all tests are conveyed to the packaging station. Depending on the market, cans are grouped in 4-packs, 6-packs, or full case trays. Robotic arms or mechanical pushers group the cans and slide them into shrink-wrap tunnels or cardboard sleeves. Once bundled, packs are palletized, either by layer robots or high-speed stackers, wrapped with stretch film and labeled with product codes, production date, and batch information. These pallets are now staged in a temperature-controlled warehouse, ready for distribution. The real-time tracking of every single ingredient, batch, fill date, and can code allows for full traceability from ingredient origin to final shipment. In the next section, we'll follow how those pallets move through the global distribution network and how Red Bull's quality assurance, shelf stability testing, and cold chain monitoring ensure that each can performs exactly as intended from Austria to Australia. With the Red Bull cans now filled, sealed, and packed onto pallets, the production process transitions into the next highly critical phase: post-production handling, distribution management, and long-term quality assurance. Although the drink is technically finished, the factory still bears significant responsibility for maintaining its integrity through storage, shipping, and shelf life. This phase involves coordinated warehouse systems, climate control, global logistics networks, and extensive quality monitoring procedures that extend well beyond the factory floor. All of it is designed to ensure that every can of Red Bull tastes and performs identically, whether it's consumed in Bangkok, Berlin, or Boston. Once the pallets are complete, they are conveyed from the packaging area into the outbound staging zone, a dedicated part of the facility built to manage finished goods. This area is laid out with barcode scanners, RFID readers, and automated warehouse software. Each pallet is scanned as it enters, recording not only the product type and production date, but also its batch code, can format, and destination market. This digital tracking ensures complete traceability of every pack produced. The system also flags any inventory that is out of rotation or that has not been cleared by the final quality audit. Pallets are stored in high bay racking systems that can reach 5 or 6 levels high. These racks are arranged to maximize airflow and minimize temperature variation, as environmental stability is critical for energy drinks. The warehouse is kept within a strict range of temperature, typically between 18 degrees C and 22 degrees C, and humidity under 60% to preserve carbonation, prevent packaging degradation, and protect flavor stability. Light exposure is minimized using tinted overhead fixtures or motion sensor lighting, since prolonged light can interact with the contents of clear or thin-walled aluminum containers, subtly affecting taste or causing internal discoloration. But before any pallet leaves the facility, it must be cleared through a final release protocol. This involves sampling from each production batch, typically 1 out of every few thousand units. These samples are sent to the in-house quality control laboratory for a battery of tests. Microbial testing is conducted to ensure that the beverage remains free from bacteria or yeast. Although Red Bull is not pasteurized, its low pH and high CO2 content provide natural protection. and the factory's sterile filling conditions act as a critical control point. Nonetheless, post-fill samples are incubated in climate-controlled chambers for 72 hours and checked for any microbial activity. Simultaneously, chemical stability tests are performed to verify that the concentrations of caffeine, taurine, sugars, acids, and vitamins are within tight tolerances. Each test is logged, reviewed, and signed off by senior lab technicians. Once the data passes review, the production batch is cleared for shipping. At this point, the factory releases the inventory into the hands of the logistics team, which organizes regional and international transportation. The Red Bull supply chain is designed around speed, efficiency, and protection. Because the drink is sold in more than 170 countries, it requires a global distribution system that can manage environmental variables, transit times, and regulatory differences across continents. Each factory or co-packing facility is paired with multiple logistics hubs, either operated directly or through third-party logistics providers, each specializing in cold chain monitoring, customs clearance, or last-mile delivery. Shipping conditions are tightly controlled. While Red Bull cans are shelf-stable and do not require refrigeration, they are sensitive to excessive heat and should not be exposed to prolonged freezing. Therefore, all transportation routes are mapped to avoid extreme temperature exposure. Trucks are preconditioned before loading, ensuring that their interior holds the correct temperature before the first pallet is moved in. During loading, factory staff monitor not just product count and pallet orientation, but also airflow paths and stacking height to ensure that cans are not crushed or deformed during transit. Each truck or container is equipped with temperature loggers and shock sensors. These devices record environmental data every few minutes and store it until offload. If a truck breaks down, or if the cargo passes through an area of extreme temperature fluctuation, the logs will show it. When the shipment arrives at its distribution center or regional warehouse, receiving teams will review the data. If it falls outside the acceptable range, the load may be held, inspected, or even rejected. This provides a full audit trail from the moment the product left the factory to its arrival at the next checkpoint. For international shipments, the process becomes even more complex. Export shipments must comply with country-specific food regulations. In some cases, ingredients must be declared differently. In others, labeling requirements vary. The factory works with regulatory teams to produce market-specific versions of the product, sometimes varying the language, caffeine content, or vitamin mix to meet local laws. Each international pallet is assigned a customs manifest, a certificate of analysis from the lab, and a temperature log that confirms it stayed within the specified range throughout the journey. Once Red Bull arrives at its destination warehouse, whether it's in Tokyo, Johannesburg, or Chicago, it enters a new round of inventory rotation and quality checks. Local distribution centers store the product under similar environmental controls, and the product is rotated using FIFO systems to minimize aging. While the drink has a long shelf life, usually around 18 months, Red Bull's internal standards aim to deliver most of its inventory to retailers within just a few weeks of production to ensure maximum freshness. Some pallets will be broken down into smaller loads and sent to large supermarket chains. Others are routed to gas stations, bars, vending machine operators, or e-commerce fulfillment centers. In each case, local merchandisers and sales teams monitor product placement, stocking practices, and display temperatures. Although Red Bull does not require refrigeration, many retailers choose to chill it for immediate consumption, and Red Bull provides branded refrigeration units to support this. At the store level, Red Bull continues to run random quality checks, known as in-market assessments. These include taste tests, packaging inspections, and code date verifications. Data from these assessments is sent back to the factory quality system and reviewed quarterly. If trends are observed, like subtle flavor degradation in warmer climates or denting during local transit, factory protocols are updated and packaging specifications may be revised. This feedback loop is critical to maintaining the uniform experience that Red Bull is known for globally. Even after the product has been sold, the process doesn't stop. Red Bull maintains traceability for every batch through lot codes printed on the bottom of each can. If a customer reports an issue, the quality team can pull that code, identify the exact production line, shift, and even the technician who oversaw that batch. While issues are rare, this system allows the company to investigate and resolve problems with precision, minimizing waste and protecting brand integrity. Beyond logistics and troubleshooting, the factory also conducts long-term aging tests. Retained samples from every production batch are stored under controlled conditions for 12 to 24 months. These samples are periodically tested for flavor consistency, vitamin retention, carbonation, and packaging durability. This helps inform decisions about shelf life labeling, new packaging materials, and product reformulation. Back at the plant, everything learned during distribution feeds into continuous improvement efforts. Engineers analyze transit shock data to refine pallet structures. Chemists review long-term flavor curves to tweak the balance of acids and preservatives. Operators attend refresher training sessions on fill line calibration, cap torque standards, and seaming pressure. The plant becomes not just a factory, but an evolving ecosystem of precision, designed to produce millions of cans with microscopic tolerance and global dependability. Inside Red Bull's production and R&D infrastructure, innovation continues quietly and continuously alongside the high-speed filling lines. While the mainstream drink is tightly standardized, parallel systems exist within the factory environment for development, testing, and controlled rollout of new variants, flavors, and formats. These operations are often confined to specialized pilot plants, small-scale, highly modular manufacturing lines where experimental recipes and new packaging concepts are trialed without disrupting the core production flow. These pilot lines mimic every critical phase of full-scale production, from batching to carbonation and filling, but at reduced volumes. Engineers can simulate the thermal and mechanical stresses of the full-size process, adjusting flow rates, temperature profiles, and equipment speeds to understand how small tweaks to formula or process could affect outcomes. Whether testing a sugar-free variation, a new flavor blend, or a limited edition can size, the data collected here determines what does and does not graduate to full factory rollout. Each new formula undergoes rigorous stress testing. Finished samples are subjected to cycles of heat, cold, vibration, and light exposure to simulate real-world transport and storage conditions. Flavor retention is tracked over time through sensory analysis and gas chromatography. Carbonation levels are monitored for stability across packaging types and temperatures. Packaging engineers assess how different aluminum can wall thicknesses or end configurations perform under pressure, especially when new recipes require modified CO2 saturation. If a variant clears all physical and chemical tests, the next step is consumer trials. In select cases, Red Bull collaborates with regional markets to test launch a new flavor or packaging size in a limited territory. These micro launches help measure demand, gather feedback, and identify operational issues before scaling up. Even then, these limited variants are often produced on flexible equipment lines reserved specifically for such runs, using interchangeable molds, modular filler heads, and smaller tank systems. Even small changes, like switching from a matte to a gloss label finish, require recalibration of the vision systems on the inspection line. Barcode scanners must be trained to detect label variations, and automated reject mechanisms must be tested to avoid false positives. This ensures no disruption in quality control, even when the product range temporarily expands. Back in the lab, teams also study ingredient interactions under extreme use scenarios. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. CAFE practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under CAFE practices, the beans are harvested, typically by hand. Hand picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, this includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers, such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin, are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 litres. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals, packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink-wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. The Coca-Cola process begins long before the beverage reaches the consumer, starting with the sourcing of raw ingredients and the preparation of the secret formula. The recipe is one of the most closely guarded trade secrets in the world, known only to a select few individuals. However, while the exact proportions of the ingredients remain undisclosed, the general components are well understood. Carbonated water, high fructose corn syrup or sugar, caramel color, phosphoric acid, natural flavors, and caffeine. The first step in manufacturing Coca-Cola is obtaining and preparing these ingredients. Water is the most important component, making up the majority of the drink. It must be purified to remove any impurities before being used in the production process. This is done through a series of filtration and purification steps, including sand filtration, carbon filtration, and reverse osmosis. These processes remove sediments, chlorine, organic compounds, and any potential contaminants, ensuring that only the purest water is used in Coca-Cola's production. The water purification process is vital because any variation in water quality could affect the final taste of the beverage. Once the water has been purified, it is ready to be mixed with the other ingredients. The syrup preparation process begins in a separate area of the factory, where high fructose corn syrup or sugar is combined with caramel coloring, phosphoric acid, and natural flavors. The caramel color gives Coca-Cola its distinct deep brown appearance, while phosphoric acid contributes to its tartness. The natural flavors used in Coca-Cola are a closely guarded secret, but they are essential in creating the beverage's unique taste. The caffeine is also added during this stage, ensuring that the drink maintains its signature stimulating effect. After the syrup is prepared, it must be carefully measured and mixed with the purified water. This is done through an automated batching system that ensures the precise ratio of syrup to water. The mixture is then subjected to a process called de-aeration, which removes any trapped air that could affect carbonation and shelf stability. This step is crucial because any excess air can lead to inconsistencies in taste and texture. Next, the mixture undergoes carbonation, one of the most important steps in the manufacturing process. Carbonation is achieved by injecting carbon dioxide into the liquid under controlled pressure and temperature conditions. The level of carbonation must be carefully calibrated to ensure that Coca-Cola has the right amount of fizziness. The CO2 used in this process is food grade and purified to remove any impurities. This step requires precision because too much or too little carbonation can alter the drink's mouthfeel and overall experience. Once the beverage has been carbonated, it is ready for bottling and packaging. However, before this can happen, the bottles or cans must be thoroughly cleaned and sterilized. This is a critical step in ensuring product safety and hygiene. Factories typically use high-pressure water jets and a sterilizing solution to clean the bottles before they are filled. Any residue or foreign particles in the bottles could compromise the quality of the drink, so this cleaning process is carefully monitored. With the bottles prepared, the filling process begins. The carbonated Coca-Cola mixture is dispensed into bottles or cans using high-speed filling machines that operate with incredible precision. The filling process must be conducted under controlled conditions to prevent foaming and loss of carbonation. The machines are designed to fill each container with the exact volume of liquid, ensuring consistency across all units. The filled bottles are then capped immediately to preserve carbonation and freshness. After capping, the bottles go through a labeling and coding process. Labels are applied to the bottles using automated machinery, and each bottle is imprinted with a date code to indicate its production date and best before date. This coding process helps with inventory management and quality control, allowing factories to track each batch of production. The labels are carefully inspected to ensure they are applied correctly, as any misaligned or missing labels can lead to packaging errors. Once labeled, the bottles move through a quality control checkpoint where they are inspected for any defects. This inspection process involves both human oversight and automated systems. High-speed cameras and sensors check for issues such as incorrect fill levels, damaged bottles, or improperly sealed caps. If any defects are detected, the affected bottles are removed from the production line to prevent them from reaching consumers. The quality control stage is one of the most critical aspects of Coca-Cola manufacturing, as it ensures that only products meeting the highest standards make it to market. After passing inspection, the bottles are packed into crates or cartons for distribution. The packaging process is fully automated, with robotic arms and conveyor belts handling the movement of products. The bottles are grouped into packs, shrink-wrapped for protection, and stacked onto pallets for transportation. The factory's logistics system ensures that the packaged products are efficiently stored and transported to distribution centers, where they are shipped to retailers, restaurants, and vending machines. The manufacturing process of Coca-Cola is designed for efficiency and precision at every stage. Factories are equipped with advanced technology and highly automated systems to ensure that production runs smoothly and consistently. Every step, from ingredient preparation to final packaging, is carefully monitored to maintain quality and safety standards. The final step before distribution involves conducting random sampling and additional quality control tests to ensure that the beverage meets Coca-Cola's strict standards. Samples are taken from each batch and tested in a laboratory for factors such as acidity, carbonation levels, and taste consistency. These tests help verify that the product remains true to Coca-Cola's signature flavor profile. If any deviations are found, adjustments are made to maintain quality. Coca-Cola factories operate around the clock, producing millions of bottles per day to meet global demand. The entire process is streamlined for maximum efficiency, ensuring that consumers receive fresh, high-quality beverages every time they purchase a bottle of Coca-Cola. The company places a strong emphasis on sustainability, incorporating water recycling and energy-efficient practices into its production processes. Water conservation efforts, CO2 recapture systems, and waste reduction initiatives help minimize the environmental impact of Coca-Cola manufacturing. Once the filled and capped bottles of Coca-Cola have undergone the initial stages of quality control, they move to an advanced inspection phase, where both automated systems and human supervisors ensure that every bottle meets the company's stringent standards. At this point, the bottles or cans are carefully checked for fill level accuracy, seal integrity, and carbonation retention. Sophisticated machines equipped with high-speed cameras analyze thousands of bottles per minute, identifying any anomalies such as underfilled or overfilled bottles, leaks, or incorrectly applied caps. If a defect is detected, the bottle is automatically removed from the production line and sent to a separate area for further evaluation. In cases where minor adjustments can be made, such as reapplying a cap that wasn't sealed properly, corrective measures are taken before the bottle is returned to the production process. However, if the defect compromises the quality of the beverage, the bottle is discarded to maintain consistency and uphold Coca-Cola's reputation for high-quality products. Parallel to this, another critical process occurs in the factory: batch testing. Randomly selected bottles from each production run are taken to an on-site laboratory, where they undergo extensive chemical and sensory analysis. Laboratory technicians assess factors such as pH levels, sugar concentration, carbonation levels, and overall taste profile to confirm that the beverage aligns perfectly with Coca-Cola's standardized formulation. Any deviation from the expected specifications results in a thorough investigation, ensuring that the issue is promptly identified and corrected. Once the bottles pass quality checks, they move on to secondary packaging. Coca-Cola is typically sold in various formats, including individual bottles, 6-packs, 12-packs, and even bulk cartons containing dozens of bottles or cans. High-speed automated packaging machines arrange the bottles into their designated configurations, wrapping them in plastic film or placing them into cardboard carriers. These machines operate with incredible precision, ensuring that every package is neatly assembled and securely sealed. At this stage, sustainability efforts come into play. Coca-Cola has invested heavily in reducing plastic waste and optimizing its packaging materials. Many of the plastic bottles used in Coca-Cola production are made from recycled PET, and the company continuously works toward increasing the percentage of recycled content in its packaging. In some regions, Coca-Cola also uses plant-based plastic materials to further minimize its environmental impact. The secondary packaging materials, such as cardboard cartons, are often sourced from recycled paper products, aligning with Coca-Cola's commitment to sustainability. Once packaged, the finished products are transported through a network of conveyor belts to a distribution staging area within the factory. Here, robotic palletizers stack the products onto pallets, organizing them efficiently for shipping. These robots use advanced algorithms to optimize space utilization, ensuring that the maximum number of products can be transported with minimal waste. The palletized products are then wrapped in protective plastic film to keep them secure during transit. The next step in the Coca-Cola manufacturing process is logistics and distribution. The company operates a vast global supply chain, with each factory producing beverages that are distributed to local and regional markets. Trucks, trains, and even cargo ships transport Coca-Cola products to distribution centers, warehouses, and retail locations around the world. The logistical network is meticulously planned to minimize transportation costs and reduce the carbon footprint of product distribution. Before shipping, warehouse personnel use barcode scanning systems and inventory management software to track every pallet of Coca-Cola. Each unit is assigned a unique barcode that corresponds to its production date, batch number, and destination. This tracking system enables the company to efficiently manage stock levels and quickly address any issues that may arise, such as recalls or shipment delays. In many cases, Coca-Cola products are delivered directly to retailers, including supermarkets, convenience stores, and vending machine operators. The company's extensive distribution network ensures that consumers can access fresh Coca-Cola virtually anywhere in the world. To maintain the freshness of the beverage, Coca-Cola implements a strict first-in, first-out inventory system, which prioritizes the sale of older stock before newer stock reaches store shelves. While Coca-Cola's distribution network ensures that the beverage reaches consumers efficiently, the manufacturing process doesn't end once the product leaves the factory. Coca-Cola factories also focus on sustainability initiatives aimed at reducing environmental impact. Water conservation is a major priority, given that water is the primary ingredient in Coca-Cola. Factories implement advanced water recycling systems, allowing them to treat and reuse water for non-product related processes such as equipment cleaning and cooling. Energy efficiency is another key focus. Many Coca-Cola plants utilize renewable energy sources, such as solar and wind power, to offset electricity consumption. The company also invests in energy-efficient machinery, reducing the overall carbon footprint of its manufacturing operations. Additionally, Coca-Cola works with local communities to support environmental sustainability initiatives such as reforestation programs and water replenishment projects. Another important aspect of Coca-Cola's manufacturing process is its adherence to strict food safety regulations. Factories comply with global food safety standards, including the Hazard Analysis and Critical Control Point System, which identifies and mitigates potential risks in food production. Employees undergo regular training on hygiene protocols, and strict sanitation measures are enforced throughout the facility. Production areas are regularly disinfected, and equipment is thoroughly cleaned after each batch to prevent cross-contamination. Coca-Cola also invests in research and development to continuously refine its production processes. Scientists and engineers work to optimize ingredient formulations, improve packaging materials, and enhance the efficiency of manufacturing operations. Innovation plays a crucial role in Coca-Cola's success, allowing the company to adapt to changing consumer preferences and market demands. For example, in response to growing health-conscious trends, Coca-Cola has introduced reduced sugar and zero sugar variants, all of which undergo the same rigorous manufacturing process as the original formula. One of the most impressive aspects of Coca-Cola's manufacturing process is its ability to maintain consistency across different regions. Regardless of where Coca-Cola is produced, whether in North America, Europe, Asia, or Africa, the taste and quality of the beverage remain the same. This consistency is achieved through strict adherence to Coca-Cola's global manufacturing standards, which dictate precise ingredient ratios, quality control measures, and production techniques. Each factory is regularly audited to ensure compliance with these standards, ensuring that consumers receive the same great-tasting Coca-Cola wherever they are in the world. Despite the high level of automation in Coca-Cola factories, human oversight remains essential. Factory workers play a crucial role in monitoring production lines, troubleshooting issues, and ensuring that operations run smoothly. From syrup blending technicians to quality control inspectors, every employee contributes to the success of the manufacturing process. Safety is also a top priority, with factories implementing comprehensive occupational health and safety programs to protect workers from potential hazards. The production of Coca-Cola is a complex and finely tuned process that extends beyond simply mixing ingredients and filling bottles. It involves numerous specialized stages that ensure the beverage maintains its signature taste, quality, and safety. As the bottled or canned Coca-Cola moves through the factory, the focus remains on maintaining efficiency, consistency, and sustainability. One of the key elements of Coca-Cola's production process is the careful management of carbonation. The carbon dioxide used to carbonate the beverage is sourced from food-grade suppliers and must meet strict purity standards. Maintaining consistent carbonation levels is critical because it affects the drink's texture, mouthfeel, and overall sensory experience. Carbonation is carefully controlled during the filling process to ensure that the right amount of CO2 is dissolved into the liquid. If the pressure or temperature is not properly maintained, the carbonation can dissipate too quickly, leading to a flat-tasting beverage. To prevent this, Coca-Cola factories use pressurized filling machines that ensure minimal CO2 loss as the beverage is transferred into bottles or cans. Once filled and capped, Coca-Cola bottles move through a final stage of quality assurance before they are packed and prepared for shipment. Each bottle is subjected to a high-speed laser inspection system that verifies the presence of the cap, ensures proper sealing, and checks for any defects in the glass or plastic. These laser inspection systems can detect even microscopic irregularities that might not be visible to the human eye, helping prevent faulty products from reaching the market. One of the most crucial aspects of Coca-Cola's manufacturing process is ensuring uniformity across all production facilities worldwide. To achieve this, the company employs a centralized quality control system that enforces strict guidelines for ingredient sourcing, syrup production, water purification, and carbonation. Each factory follows a standardized protocol, and periodic audits are conducted to verify compliance. This rigorous attention to detail ensures that a bottle of Coca-Cola produced in the United States tastes identical to one manufactured in Japan, South Africa, or Brazil. While consistency is a priority, Coca-Cola also tailors its formulation slightly to accommodate regional preferences and regulatory requirements. In some countries, the beverage is sweetened with high fructose corn syrup, while in others, cane sugar is used. Additionally, the amount of caffeine in the beverage may vary slightly depending on local guidelines. Despite these subtle differences, the core flavor profile remains the same, thanks to the precise blending of the secret formula. After passing through final quality control checks, Coca-Cola bottles and cans are directed toward packaging and palletizing. At this stage, packaging automation plays a key role in optimizing efficiency. Modern Coca-Cola factories use robotic arms and conveyor systems to sort, pack, and shrink wrap the products into multi-packs, cases, or crates. These machines work at incredible speeds, sometimes processing thousands of bottles per minute. Sustainability efforts are heavily integrated into the packaging process. Coca-Cola has made significant strides in reducing its environmental impact by using lightweight packaging materials, increasing the use of recycled plastics, and investing in refillable bottle programs. Many Coca-Cola factories have adopted a closed-loop recycling system in which used plastic bottles are collected, cleaned, and reprocessed into new bottles. This reduces reliance on virgin plastic and minimizes waste. Once the Coca-Cola products are packed and palletized, they are moved to the warehouse storage area within the factory. This area is carefully temperature controlled to preserve the beverage's freshness and carbonation levels. Coca-Cola's warehouse management system tracks each pallet's movement, ensuring that products are stored efficiently and dispatched in a timely manner. From the warehouse, Coca-Cola products are distributed through a highly organized logistics network. The company utilizes a combination of trucks, rail transport, and shipping containers to move its products from manufacturing facilities to regional distribution centers. These centers act as hubs that supply retailers, restaurants, and vending machines with fresh stock. Coca-Cola's logistics team uses advanced forecasting software to predict demand and optimize delivery routes, reducing fuel consumption and improving efficiency. Once Coca-Cola reaches retail locations, the company's work is not finished. Coca-Cola employs a global network of merchandising teams that ensure products are displayed prominently in stores, kept at the right temperature, and stocked in vending machines and coolers. These teams also monitor product rotation, ensuring that older stock is sold first to maintain freshness. Another key element in Coca-Cola's manufacturing and distribution process is its commitment to reducing water usage. Water stewardship is a major initiative for Coca-Cola, as the company relies heavily on water as its primary ingredient. Many Coca-Cola plants have implemented state-of-the-art water reclamation systems that allow them to recycle and reuse water in non-product applications such as equipment cooling and bottle washing. These efforts help minimize water waste and ensure responsible water management. In addition to water conservation, Coca-Cola has also invested in reducing its overall carbon footprint. Many of its manufacturing plants have adopted energy-efficient technologies, including solar panels, wind turbines, and advanced heat recovery systems. These measures help Coca-Cola decrease its reliance on fossil fuels, and reduce greenhouse gas emissions. The company has also transitioned many of its delivery trucks to hybrid or electric models to further lower its environmental impact. While Coca-Cola's manufacturing process is highly automated, it still requires a skilled workforce to oversee operations. Factory employees play a crucial role in maintaining equipment, monitoring production lines, and conducting quality checks. They receive extensive training to ensure they understand food safety protocols, machinery operation, and emergency procedures. Coca-Cola places a strong emphasis on worker safety, implementing strict guidelines to protect employees from potential hazards associated with high-speed machinery and industrial production environments. The level of precision required to produce Coca-Cola at such a massive scale is truly remarkable. Every ingredient, every machine, and every worker plays a vital role in ensuring that millions of bottles of Coca-Cola can be produced and distributed each day without compromising quality. The company's ability to manufacture its beverage with such consistency across different regions is a testament to the effectiveness of its standardized processes and advanced technology. Coca-Cola's manufacturing journey doesn't end once the product reaches consumers. The company continues to innovate, finding new ways to improve its production methods, reduce its environmental impact, and adapt to changing consumer preferences. Recent innovations include the development of plant-based plastic bottles, the introduction of lower-calorie and sugar-free alternatives, and improvements in energy-efficient bottling techniques. As Coca-Cola's manufacturing process continues beyond the bottling and packaging stages, the company remains focused on optimizing efficiency, reducing waste, and ensuring that every bottle that reaches the consumer meets its high standards. With millions of bottles and cans produced daily in factories around the world, Coca-Cola relies on a seamless integration of automated systems, rigorous quality control, and strategic logistics to maintain its position as one of the most recognizable beverages on the planet. One of the most important aspects of Coca-Cola's production process is its supply chain management. The company sources its ingredients from a global network of suppliers, ensuring that its factories receive high-quality raw materials consistently. The supply chain involves the coordinated movement of sugar or high-fructose corn syrup, caffeine, caramel coloring, phosphoric acid, and natural flavorings, all of which must be stored under precise conditions to maintain their integrity. The syrup used to create Coca-Cola is produced in specialized facilities known as concentrate plants. These plants manufacture the highly concentrated base syrup, which is then shipped to bottling facilities worldwide, where it is mixed with purified water and carbonated before packaging. Once the concentrate reaches the bottling plant, it is diluted with purified water following Coca-Cola's standardized formulation. The water undergoes extensive treatment to remove any impurities, ensuring that the final beverage maintains the same taste, regardless of where it is produced. The carbonation process is carefully monitored, as even a slight variation in CO2 levels can affect the drink's mouthfeel and effervescence. Coca-Cola's research and development teams continuously refine the carbonation techniques to ensure the perfect balance of bubbles in every sip. With the beverage ready for packaging, Coca-Cola utilizes a diverse range of bottling formats to cater to different consumer preferences. The company produces its beverages in glass bottles, aluminum cans, and PET plastic bottles, each with its own specific manufacturing process. Glass bottles, for example, require a specialized filling line that ensures the bottles are sterilized before filling, capped securely, and transported safely. PET bottles undergo a process called blow molding, in which small preforms of plastic are heated and expanded into the shape of a full-sized bottle using high-pressure air. This method allows Coca-Cola to produce lightweight, durable bottles that are both cost-effective and recyclable. As the bottles and cans move through the high-speed production lines, they are continuously monitored by automated inspection systems. These systems use infrared sensors, X-ray technology, and high-speed cameras to detect any irregularities in fill levels, cap placement, and structural integrity. Bottles that do not meet Coca-Cola's quality standards are automatically removed from the line and discarded or recycled. This attention to detail ensures that only perfect products reach consumers. After being filled, capped, and labeled, Coca-Cola products are assembled into multi-packs or crates for easier handling and distribution. The packaging process is designed for maximum efficiency, with robotic arms swiftly arranging the bottles into their respective cases. Sustainability remains a key focus during this stage, with Coca-Cola implementing measures to reduce plastic waste by using lightweight packaging materials and increasing the use of recycled content. Many Coca-Cola plants have adopted a closed-loop recycling system, in which post-consumer PET bottles are collected, cleaned, and transformed into new bottles. This initiative significantly reduces the company's reliance on virgin plastics and helps minimize environmental impact. Once packaged, the products are transported to warehouse storage areas, where they are organized based on expiration dates and distribution routes. Coca-Cola follows a strict first in, first out inventory system to ensure that older stock is shipped out before newer stock, preventing waste and maintaining freshness. The company's advanced inventory management system tracks every case, ensuring that retailers receive the right products at the right time. From the warehouse, Coca-Cola products embark on their journey to retailers, supermarkets, vending machines, and restaurants. The company's logistics team meticulously plans transportation routes to optimize delivery efficiency and reduce fuel consumption. Coca-Cola operates a fleet of delivery trucks, many of which are equipped with refrigeration units to keep beverages cool during transit. In some regions, Coca-Cola has introduced electric delivery trucks to further minimize its carbon footprint. While Coca-Cola's production process is largely automated, human oversight remains essential at every stage. Factory employees play a critical role in ensuring that operations run smoothly, troubleshooting machinery issues, and maintaining stringent hygiene standards. Workers undergo regular training to stay up to date with food safety protocols, equipment operation, and emergency response procedures. The company prioritizes worker safety, implementing strict guidelines to protect employees from potential hazards associated with high-speed production lines and industrial equipment. Coca-Cola's commitment to sustainability extends beyond its factories and supply chain. The company actively invests in water conservation projects, renewable energy initiatives, and recycling programs to reduce its overall environmental impact. In many regions, Coca-Cola collaborates with local communities to replenish water sources and support biodiversity conservation efforts. For every liter of water used in its production process, Coca-Cola works to return an equivalent amount to the environment through water stewardship initiatives. Another area of continuous improvement within Coca-Cola's manufacturing process is the development of innovative beverage formulations. In response to evolving consumer preferences, Coca-Cola has expanded its product portfolio to include sugar-free and low-calorie alternatives. The production of these variations follows a similar process to the original formula, with slight adjustments made to accommodate different sweeteners and flavor profiles. The introduction of Coca-Cola Zero Sugar and Diet Coke has required modifications to syrup formulation and taste testing procedures to ensure that these alternatives maintain the same crisp, refreshing experience as the classic version. Beyond traditional retail, Coca-Cola is also distributed through vending machines and fountain dispensers. The production of Coca-Cola syrup for fountain machines follows a slightly different process, as the syrup is shipped in concentrated form to restaurants and fast food chains, where it is mixed with carbonated water on site. This method allows for efficient storage, and reduces packaging waste. The creation of Fanta inside a factory is a meticulous and finely tuned process involving chemistry, engineering, and strict quality control to ensure every bottle delivers the same bold, fruity flavor. Unlike some beverages that rely on a single uniform recipe, Fanta is produced in multiple flavors, each requiring its own balance of ingredients. This makes the production process both complex and fascinating, as every step must be carefully managed to maintain consistency and freshness across different variations. It all begins with the selection and preparation of ingredients. The core elements of Fanta include water, sweeteners, fruit flavorings, citric acid for tartness, preservatives to maintain shelf life, and carbon dioxide to give the drink its signature fizziness. However, each flavor, such as orange, grape, pineapple, or strawberry, requires a different combination of fruit extracts, natural or artificial colorings, and acidity regulators. These ingredients must meet strict quality and safety standards before they can be used in production. Water, being the main component of Fanta, is the first ingredient to be processed. The quality of the water used in soft drinks plays a crucial role in the final product's taste, clarity, and stability. Factories receive water from local sources, but before it can be used, it must go through an extensive purification process. This process begins with coarse filtration, where large particles, sediments, and debris are removed. The water is then passed through activated carbon filters to eliminate organic compounds, chlorine, and any undesirable odors or tastes. Finally, a reverse osmosis system is used to ensure the highest level of purity. This stage is critical because even the slightest variation in water quality can alter the flavor profile of Fanta. While the water undergoes purification, the syrup production process begins. This is where Fanta's distinctive flavor is created. In large mixing tanks, the essential ingredients are blended to form a concentrated syrup. Each flavor variation has its own unique formulation, requiring precise measurements of fruit extracts, sweeteners, and acids. Citric acid is commonly used to provide a tartness that enhances the fruity taste, while different natural and artificial flavorings are combined to create the signature taste of each Fanta variety. Sweeteners play an essential role in balancing the overall flavor. Depending on the region, the factory may use high fructose corn syrup, cane sugar, or alternative sweeteners such as aspartame for sugar-free versions. The exact ratio of sweetener to other ingredients must be meticulously controlled, as too much or too little can dramatically affect the drink's taste and mouthfeel. Once the syrup is mixed, it undergoes a process called homogenization. This ensures that all the ingredients are evenly dispersed and that no separation occurs during storage. The syrup is then transferred to large storage tanks, where it is kept under strictly controlled conditions before being combined with purified water. These tanks are equipped with continuous mixing systems to prevent any settling or inconsistencies in the formula. At this point, the production process moves to the batching stage, where the syrup is mixed with purified water in exact proportions. The goal here is to dilute the concentrated syrup to the precise flavor concentration required for Fanta. The ratio of syrup to water must be carefully maintained, as even a small deviation could result in a drink that is too strong or too weak in flavor. This blending process takes place in specially designed tanks, where the mixture is continuously stirred to ensure uniformity. While the flavor base is being prepared, another critical step is underway: deaeration. Deaeration is the process of removing excess oxygen from the liquid before carbonation takes place. If too much oxygen remains in the mixture, it can affect the beverage's stability, leading to unwanted changes in taste and shelf life. The deaeration process occurs under vacuum conditions, pulling out any dissolved air and preparing the liquid for the next crucial phase: Carbonation. Carbonation is what gives Fanta its characteristic fizz. This step involves the careful infusion of carbon dioxide gas into the liquid under controlled pressure and temperature. The conditions must be just right, as the solubility of CO2 depends on temperature and pressure levels. If the carbonation process is not precise, the drink may become too flat or overly fizzy, both of which can negatively impact the consumer experience. The level of carbonation is carefully calibrated for each variety of Fanta, as some flavors require a different mouthfeel to enhance their particular fruit notes. Meanwhile, quality control tests are performed at every stage of production to ensure that the beverage meets strict consistency and safety standards. Samples from each batch are taken to an on-site laboratory where they are analyzed for acidity levels, sugar content, and overall taste. Highly trained technicians conduct these tests using specialized equipment to confirm that every batch meets the exact specifications required. If any deviation is detected, adjustments are made immediately before the product moves further along the production line. At this stage, the Fanta mixture is nearly complete, but it still has to be monitored for consistency before it can proceed to bottling. The temperature of the liquid must be kept within an optimal range to ensure the carbonation remains stable. If the temperature fluctuates too much, carbon dioxide may escape, resulting in a less fizzy drink. Advanced monitoring systems are used to track and adjust these conditions in real time, ensuring that the beverage is ready for the next stage of production. While the main beverage formulation is being perfected, the factory is simultaneously preparing the bottles and cans that will hold the finished product. Modern beverage production facilities use an advanced system for bottle manufacturing and preparation. For plastic bottles, the process begins with small PT preforms that are heated and expanded into their final shape using high-pressure air in a process called blow molding. This allows the factory to produce lightweight, durable bottles on-site, reducing the need for external suppliers and increasing efficiency. Glass bottles and aluminum cans follow a different preparation process. They are delivered to the factory pre-made and must undergo thorough cleaning and sterilization before being used. Each bottle or can is subjected to a high-pressure rinse with purified water and a sanitizing solution to remove any potential contaminants. Strict hygiene protocols ensure that every container is completely sterile before it reaches the filling stage. At this point in the production process, everything is coming together. The beverage is fully mixed, carbonated, and quality tested, while the bottles and cans are ready for filling. However, there are still multiple steps left to ensure that every bottle of Fanta meets the highest production standards. The next stage will involve high-speed filling, sealing, labeling, and additional quality control checks before the finished product is packaged and prepared for distribution. As the production line continues, the coordination of multiple systems working in perfect harmony becomes apparent. Every ingredient, machine, and quality control checkpoint plays a role in making sure that Fanta reaches consumers in the best possible condition. This highly organized process reflects the complexity behind what may seem like a simple bottle of fruity, fizzy refreshment. With the Fanta mixture fully prepared, carbonated, and quality tested, the production process moves toward the next major stage, the filling and bottling process. This part of manufacturing is one of the most crucial, as it requires absolute precision to ensure that every bottle or can is filled to the correct level, sealed properly, and protected from any external contamination. The entire operation is designed for efficiency, with high-speed machinery handling thousands of units per hour. Before the filling process can begin, the bottles and cans must be ready to receive the beverage. If plastic bottles are used, they have already gone through the blow molding process, where PET preforms are heated and expanded into their final shape. These bottles are lightweight, durable, and designed to withstand the pressure of carbonation. Glass bottles, on the other hand, arrive at the factory pre-made and must go through a thorough cleaning and sterilization process before being used. Similarly, aluminum cans are delivered in bulk and are also washed and sanitized to ensure absolute cleanliness. The sterilization process for bottles and cans is highly controlled. Each container is subjected to a series of high-pressure water jets and steam treatments, removing any potential contaminants that could affect the final product. In addition to physical cleaning, a chemical sanitization step is included, ensuring that no bacteria, dust, or residue remains inside the containers. Any bottle or can that fails to pass the cleanliness check is removed from the line and sent for reprocessing or disposal. Once the bottles and cans are verified as clean and sterile, they move along the production line toward the filling machines. These machines are designed to dispense the Fanta mixture with extreme precision, ensuring that each container receives exactly the right amount of liquid. The filling process must also take into account the carbonation level of the beverage. Since Fanta is a carbonated drink, the liquid is dispensed in a way that prevents excessive foaming and preserves the right amount of carbon dioxide. This is achieved through a pressurized filling system that maintains the carbonation inside the liquid as it is transferred into the bottles and cans. Different types of filling systems are used depending on the packaging format. For plastic bottles, a gravity filling system is often used, allowing the liquid to flow smoothly into the bottles while maintaining precise volume control. For aluminum cans, a counter-pressure filling system is more common, as it helps retain carbonation and prevent spillage. Regardless of the method, the goal is to ensure that each unit is filled with the same exact volume of Fanta while maintaining its fizziness and freshness. Once the bottles and cans are filled, they move to the capping and sealing station. This step must be completed almost instantly after filling to prevent any loss of carbonation. Plastic bottles are sealed with screw-on caps, which are applied using high-speed capping machines that tightly secure each cap onto the bottle's neck. These caps are designed to hold in the pressure from carbonation, ensuring that the drink remains fizzy until opened by the consumer. For glass bottles, a crimped metal cap, often called a crown cap, is used. These caps are pressed onto the bottle opening with a strong mechanical force, creating an airtight seal. The use of crown caps ensures that the carbonation remains intact, preventing any loss of fizz over time. Meanwhile, aluminum cans are sealed with pull tab lids, which are crimped onto the can opening to create a pressurized seal. The precision required for this step is immense, as even the slightest sealing error can lead to leaks or loss of carbonation. With the bottles and cans now sealed, the next stage in the production process is labeling and batch coding. Labels are an essential part of Fanta's branding, providing consumers with product information, flavor identification, and branding visuals. The labeling process is highly automated, with machines applying labels to bottles at high speeds. These labels must be aligned perfectly, as any misalignment could make the product appear unprofessional or difficult to identify on store shelves. In addition to labels, each bottle and can receives a batch code, typically printed using a laser or inkjet printer. This code includes details such as the production date, expiration date, and batch number. The purpose of this coding is to allow for easy traceability in case of any quality issues. If a batch is found to have any defects, the factory can quickly identify and recall only the affected products, minimizing waste and ensuring consumer safety. Now that the filled and sealed Fanta bottles and cans have been labeled and coded, they move on to the final inspection phase. This is one of the most important parts of the entire manufacturing process, as it ensures that every single unit meets strict quality control standards. Advanced inspection systems are used to detect any defects in the bottles, cans, or caps. high-speed cameras and laser sensors scan each product to check for issues such as improper sealing, incorrect fill levels, label misalignment, or damaged packaging. Any defective products that do not meet quality standards are automatically removed from the production line. This ensures that only perfect, high-quality Fanta reaches consumers. The rejected bottles and cans are sent to a separate area for recycling or disposal, depending on the nature of the defect. If the issue is a minor one, such as a misaligned label, the product may be corrected and reintroduced to the production line. Once the final inspection is complete, the ready-to-ship bottles and cans are transported to the packaging area. This is where they are grouped into multi-packs or placed in cartons for easier distribution. The packaging process is fully automated, with robotic arms handling the placement of bottles into trays, shrink-wrapping multi-packs, and stacking cases onto pallets. The type of packaging used depends on the market. In some regions, Fanta is commonly sold in large multi-packs wrapped in plastic film, while in others, cardboard cartons are used to hold smaller packs together. Sustainability plays a significant role in Fanta's packaging process. Many of the plastic bottles used are made from recycled PET, which reduces plastic waste and environmental impact. Factories are continuously working to reduce plastic usage by making bottles lighter while maintaining their durability. Similarly, paper-based packaging materials are sourced from sustainable forests to ensure that the environmental footprint of production remains as low as possible. Once packaged, the finished products are transported to storage areas within the factory. These areas are climate controlled to maintain the freshness and quality of the beverages before they are shipped out to retailers. The inventory system used in the warehouse tracks every pallet of Fanta, ensuring that stock is rotated properly to maintain freshness. Products are organized based on their production dates, with older stock being distributed first to ensure that consumers always receive the freshest possible drinks. With Fanta now fully produced, filled, sealed, labeled, inspected, and packaged, the next stage of its journey involves logistics and distribution. Trucks, trains, and cargo containers are used to transport the beverages to supermarkets, vending machines, convenience stores, and restaurants. The logistics process must be carefully managed to ensure that Fanta reaches its destination in perfect condition without any loss of carbonation or freshness. The transition from the production line to distribution requires careful handling to ensure that every bottle and can maintains its quality from the factory to the consumer. Despite the high levels of automation in the manufacturing process, this stage still requires a combination of technology, planning, and human oversight to maintain efficiency. As soon as Fanta bottles and cans are packaged, they are transported via conveyor belts to a dedicated storage area within the factory. These warehouse zones are carefully climate controlled to prevent any degradation in quality. Since Fanta is a carbonated beverage, it must be kept at optimal temperatures to ensure that the carbonation remains stable and does not dissipate before consumption. Any exposure to excessive heat or fluctuating temperatures could lead to pressure changes inside the bottles and cans, potentially affecting the taste and texture of the drink. Warehouses use an advanced inventory tracking system to monitor the movement of every batch of Fanta that is produced. Barcodes or QR codes on the packaging allow for real-time scanning and tracking, ensuring that each unit is logged into the system. This technology helps maintain an efficient first-in, first-out system, where older stock is shipped out first to ensure freshness. The software also helps manage supply and demand, ensuring that production aligns with market needs and avoiding unnecessary overproduction. During this stage, quality control does not stop. Factory personnel conduct regular spot checks, examining random samples from different batches to ensure that the carbonation levels, flavor, and overall integrity of the product remain consistent. If any inconsistencies are detected, the affected batch is. The process begins with water, which forms the base of cherry Coca-Cola. It's not just any water that can be used. It must be highly purified to ensure no off-tastes or impurities interfere with the final product. Upon arrival at the factory, water undergoes a multi-step purification process. First, it is passed through large sand filters to remove visible debris and particulate matter. Next, it moves through activated carbon filters, which strip out chlorine and other organic compounds that could affect the drink's flavor. This step is crucial in ensuring a neutral tasting base. After this, reverse osmosis or microfiltration is employed to remove microscopic contaminants, bacteria, and dissolved minerals. This purified water is continuously tested for pH balance and purity before being approved for use. Now, it's time to introduce the sweeteners, which are responsible for cherry Coca-Cola's characteristic sweetness. The type of sweetener used depends on the region. In North America, high fructose corn syrup is the primary choice due to its affordability and efficient blending properties. In other regions, sucrose from sugarcane or sugar beets is used. HFCS is produced through an enzymatic conversion process that transforms cornstarch into glucose and then into fructose, creating a highly soluble and sweet liquid. The syrup, or sucrose, is delivered in tanker trucks and stored in large stainless steel silos within the factory. Before use, the sweetener is filtered and preheated to ensure it integrates seamlessly with the rest of the ingredients. The next essential ingredient is phosphoric acid, which gives cherry Coca-Cola its slight tang and acts as a preservative. Phosphoric acid is sourced from phosphate rock, which is treated with sulfuric acid to produce a food-grade acid that can be used in soft drinks. This ingredient arrives at the factory in concentrated liquid form and is stored in specialized tanks to prevent contamination. Precision is key when adding phosphoric acid. Even a slight variation in concentration can alter the drink's flavor balance, making it too tart or too flat. Caffeine, another critical component, is added to provide the beverage's stimulating effect. The caffeine used in cherry Coca-Cola is either extracted from coffee beans and tea leaves or synthesized in laboratories to maintain consistency. It arrives in powdered form and must be carefully measured before being dissolved into the syrup mixture. One of the most recognizable aspects of cherry Coca-Cola is its deep brown color, which is achieved using caramel color. Caramel color is made by heating sugar compounds with acids or alkalis, creating a complex mixture of caramelized sugars that provide both color and subtle bitter notes that complement the drink's sweetness. Caramel color must be carefully controlled for shade consistency, ensuring that every batch of cherry Coca-Cola has the same appearance. Now, it's time to add the proprietary natural flavors that define Coca-Cola's unmistakable taste. These flavors, known internally as Merchandise 7X, are a carefully guarded secret, containing a mix of citrus oils, spices, and herbal extracts. The precise blend is known only to a handful of people within the Coca-Cola company. These concentrated flavoring agents are added in precise amounts, ensuring the signature cola taste remains identical across all global production sites. But what truly differentiates cherry Coca-Cola from its classic counterpart is the cherry flavoring. This is created using natural cherry extracts or synthetic cherry compounds, depending on local regulations and supply chain availability. Natural cherry extracts are obtained through cold pressing ripe cherries to capture their essence, while synthetic cherry flavors replicate the fruity, slightly tart taste using chemical compounds such as benzaldehyde. The cherry flavor must be added in a carefully measured amount to create a perfect balance with the cola notes without overpowering them. Once all the ingredients have been sourced, purified, and prepared, it's time for the next step, creating the concentrated syrup. In a dedicated syrup production area of the factory, Large stainless steel mixing tanks equipped with powerful agitators are used to blend the ingredients into a homogeneous mixture. The process starts by heating the purified water slightly to improve ingredient solubility. The sweetener, whether HFCS or sucrose, is then gradually introduced while the mixture is stirred continuously to prevent crystallization. Next, the phosphoric acid is added, providing cherry Coca-Cola with its signature tangy undertone. Because phosphoric acid is highly concentrated, automated dosing systems are used to ensure precise measurement, preventing any deviations in taste. Following this, the caffeine is dissolved in a small amount of warm water before being incorporated into the syrup, ensuring even distribution throughout the mixture. The natural flavors, including the merchandise 7X blend and cherry flavoring, are then carefully added. These flavor components are typically pre-mixed into an emulsified solution to ensure they disperse evenly throughout the syrup. This step is crucial, as any inconsistencies in flavor distribution can lead to variations in taste between different production batches. Finally, the caramel color is introduced, giving cherry Coca-Cola its signature appearance. Once all the ingredients are combined, the syrup undergoes a multi-stage filtration process to remove any undissolved particles. This is typically done using fine mesh filters or centrifugal separation methods, ensuring that the syrup is smooth and free from any impurities. After filtration, the syrup is transferred to holding tanks, where it is kept under controlled conditions before being sent to the bottling stage. Throughout the syrup production process, quality control plays a vital role. Factory workers take samples from each batch and conduct tests to measure sweetness levels, acidity, and overall flavor consistency. Sensory panels, trained employees who specialize in taste testing, evaluate the syrup to ensure it matches the established cherry Coca-Cola flavor profile. If any discrepancies are detected, adjustments are made before the syrup is approved for bottling. With the syrup now fully prepared, the next step is dilution, carbonation, and bottling. This is where the concentrated syrup is combined with carbonated water and packaged into cans and bottles for distribution worldwide. But before we get to that, the syrup must first be transported to the filling stations in a highly controlled manner. The next phase of production ensures that the correct syrup-to-water ratio is maintained and that the carbonation process delivers the signature effervescence that makes cherry Coca-Cola such a refreshing drink. Now that the syrup is ready, it's time to move on to the next critical stage, blending the syrup with carbonated water and ensuring that the correct levels of fizziness, taste, and consistency are achieved in every bottle and can. This process is where cherry Coca-Cola transforms from a concentrated mixture into the refreshing, bubbly beverage that millions of consumers enjoy. Now that the concentrated cherry Coca-Cola syrup is fully prepared and stored under controlled conditions, it's time to move on to the next crucial step in the manufacturing process: blending the syrup with carbonated water and ensuring the perfect level of fizziness. This stage is where cherry Coca-Cola takes its final form, transforming from a concentrated mixture into the refreshing, bubbly beverage that millions of people enjoy. The precision involved in this step is critical because even slight inconsistencies in carbonation or syrup dilution can result in an off-tasting product. The process begins with the careful transportation of the concentrated syrup to the filling stations. To prevent contamination and maintain consistency, the syrup is pumped through stainless steel pipes from the storage tanks to a specialized mixing unit known as a proportioner. The proportioner is one of the most vital machines in the entire production line, as it precisely controls the ratio of syrup to water. Cherry Coca-Cola's signature taste depends on the exact balance of ingredients, and any deviation in the syrup to water ratio could result in an overly sweet or weak-tasting beverage. The standard ratio for Coca-Cola products is approximately 1 part syrup to 5 parts carbonated water, but this can vary slightly depending on factors such as temperature and altitude, which can affect carbonation retention. Before the syrup and water are combined, the water must undergo a final round of purification to ensure absolute consistency. Even though the water has already been filtered and purified at the beginning of the process, additional treatment steps are performed just before carbonation. The water is passed through activated carbon filters once more to remove any remaining traces of chlorine or organic matter. Then it is chilled to a precise temperature, usually around 1 to 3 degrees Celsius. Chilling the water at this stage is essential because cold liquid absorbs carbon dioxide more efficiently, which results in finer and longer-lasting bubbles in the final product. Now comes the most intricate step: carbonation. The carbonation process is what gives cherry Coca-Cola its signature fizz and enhances the overall drinking experience. Carbon dioxide gas is injected into the chilled water under high pressure using specialized carbonation tanks. These tanks are equipped with fine diffusion plates that allow the gas to dissolve evenly into the liquid, ensuring consistent carbonation levels throughout the entire batch. The CO2 used in this process must be of food-grade quality, free from impurities that could alter the beverage's taste. To maintain the ideal carbonation level, the process is carefully controlled using high-precision sensors that monitor temperature, pressure, and CO2 concentration in real time. Once the water is fully carbonated, it is immediately mixed with the concentrated cherry Coca-Cola syrup inside the proportioner. This must be done swiftly to prevent any loss of carbonation. The high-speed blending process ensures that the syrup and carbonated water mix thoroughly without causing excessive foaming, which could lead to product loss. As soon as the mixture is complete, the freshly carbonated cherry Coca-Cola is sent directly to the filling lines for packaging. However, this must be done under strictly controlled conditions to maintain carbonation and prevent oxidation, which could negatively affect the beverage's taste and shelf life. The next step is the bottling and canning process, where the freshly mixed cherry Coca-Cola is transferred into its final packaging. This stage of production requires highly specialized machinery that can fill thousands of bottles and cans per minute while maintaining product integrity. The bottling and canning lines operate at incredible speeds, and every detail, from the fill level to the sealing process, must be executed with extreme precision. The filling process begins with the preparation of the containers. Whether the product is being packaged in aluminum cans, plastic PET bottles, or glass bottles, each type of packaging undergoes a thorough cleaning and sterilization process before being filled. In the case of aluminum cans, they arrive at the factory in bulk and are depalletized before being sent through an inverted high-pressure air rinsing system that removes any dust or debris. For PET and glass bottles, the process is more intensive. PET bottles are first blown into shape from preforms using heated molds, while glass bottles go through a multi-step washing process that includes detergent cleaning, high-temperature rinsing, and sterilization with ozone-treated water. Once the containers are sanitized and ready for filling, they move along conveyor belts to the high-speed filling machines. These machines operate with incredible efficiency, using precision nozzles to dispense the exact amount of cherry Coca-Cola into each container. One of the biggest challenges in this step is ensuring that carbonation is preserved during filling. To prevent excessive foaming and carbonation loss, the filling machines use counter-pressure technology. This involves pressurizing the container with CO2 before filling it with the beverage, ensuring that the carbonation remains intact and that there is minimal oxygen exposure. As the bottles and cans are filled, they are closely monitored by sensors and automated quality control systems to ensure that the correct fill levels are maintained. Any underfilled or overfilled containers are automatically rejected from the line. The next critical step is sealing, where each container is securely closed to lock in freshness. For aluminum cans, an automated seaming machine places a lid on top of the can and crimps it into place, creating an airtight seal. For plastic bottles, tamper-evident caps are applied using high-speed capping machines, while glass bottles are typically sealed with either twist-off metal caps or traditional crown caps. Immediately after sealing, the filled containers go through a pasteurization or cold sterilization process depending on the packaging type and regional regulations. In some cases, cherry Coca-Cola undergoes flash pasteurization, where the beverage is rapidly heated and cooled to kill any potential microorganisms without altering the taste. However, for many markets, Coca-Cola products are aseptically filled, meaning that the entire bottling process is conducted under sterile conditions, eliminating the need for heat treatment. Once the sealing and sterilization process is complete, the bottles and cans move to the labeling and packaging stage. This is where branding and product information are applied to each container, ensuring that the final product meets regulatory requirements and maintains Coca-Cola's iconic visual identity. Now that the cherry Coca-Cola has been bottled and sealed, the next phase of the manufacturing process focuses on quality control and inspection. Every single can and bottle must meet Coca-Cola's strict global quality standards before it can be shipped to retailers. This process involves multiple layers of testing, from automated inspections on the production line to detailed laboratory analysis conducted by food scientists. Even the smallest deviation in taste, carbonation level, or packaging integrity can result in a batch being rejected, ensuring that only the highest quality product reaches consumers. The first step in quality control takes place immediately after the filling and sealing process. High-speed vision inspection systems are installed along the conveyor belts, using advanced cameras and sensors to examine each bottle and can for defects. These systems check for issues such as underfilled or overfilled containers, misaligned caps, dents in cans, or improperly applied labels. If a container does not meet specifications, it is automatically removed from the line by a rejection mechanism. This automated inspection process allows for the real-time elimination of defective products, preventing inconsistencies from reaching the market. Another crucial quality control measure is the carbonation and pressure test. Since cherry Coca-Cola's signature fizz is one of its defining characteristics, it is essential to ensure that each bottle and can contains the correct amount of dissolved CO2. To verify this, a random selection of containers is taken off the production line and placed into a specialized testing chamber where their internal pressure is measured. If the pressure falls outside the acceptable range, this could indicate improper carbonation levels, a sealing defect, or temperature fluctuations during the filling process. If an issue is detected, adjustments are made to the carbonation equipment to maintain consistency across the batch. Next, samples from each production run are sent to the on-site laboratory for detailed chemical and sensory analysis. Here, trained food scientists perform a variety of tests to confirm that the cherry Coca-Cola meets Coca-Cola's strict formulation guidelines. One of the first tests conducted is the Brix test, which measures the concentration of dissolved sugars in the beverage. Since cherry Coca-Cola has a carefully calibrated sweetness level, any deviation in the Brix measurement could indicate an incorrect syrup-to-water ratio, requiring adjustments in the proportioner. Another key laboratory test is pH analysis. The acidity of cherry Coca-Cola is a crucial component of its taste, and this is largely controlled by the phosphoric acid content. A pH meter is used to measure the beverage's acidity, ensuring that it falls within the required range. Any variation in pH can significantly affect the drink's flavor balance, so this test is performed regularly to maintain consistency. Sensory evaluation is another critical aspect of quality control. A panel of trained taste testers, known as a sensory panel, is responsible for conducting blind taste tests to ensure that each batch of cherry Coca-Cola matches the expected flavor profile. These experts are highly trained to detect even the slightest differences in sweetness, acidity, carbonation, and cherry flavor intensity. They compare samples from the production line with reference samples from previous batches, ensuring that the taste remains uniform across all locations. If any inconsistencies are detected, adjustments are made to the formulation or processing parameters before the product is released for distribution. Packaging integrity is also a major focus of the quality control process. Even if the beverage itself meets all specifications, the packaging must be flawless to ensure product safety and shelf stability. To test this, random samples of filled bottles and cans undergo extreme stress testing. For plastic bottles, drop tests are conducted to simulate potential impacts during transportation. The bottles are dropped from various heights to ensure that they do not crack, leak, or experience cap failure. Cans are subjected to compression tests, where a machine applies controlled pressure to verify their structural integrity. If a can is too weak, it could deform or burst under normal handling conditions. If it is too rigid, it could indicate an issue with the aluminum thickness or the pressurization process. These tests help ensure that every container is durable enough to withstand shipping, storage, and handling by consumers. Another important quality control step is microbiological testing. Although cherry Coca-Cola's high acidity and carbonation naturally inhibit microbial growth, samples are still tested for the presence of bacteria, yeast, or mold. Microbiological testing is performed in a sterile laboratory environment where beverage samples are incubated under controlled conditions to detect any signs of microbial contamination. Even though Coca-Cola products are manufactured in sterile conditions, this extra layer of safety ensures that no contamination occurs at any stage of production. After all of these quality control tests have been completed, the final step before distribution is the batch coding and tracking process. Each bottle and can is printed with a unique production code that contains information about the manufacturing date, production line, and facility location. This allows Coca-Cola to track every product from the factory to store shelves. If an issue is ever discovered in a specific batch, this coding system enables rapid identification and recall of affected products. Once the cherry Coca-Cola has passed all quality control tests, the final phase of production involves packaging and distribution. This step ensures that the product is properly grouped, protected, and efficiently transported from the factory to retailers worldwide. The packaging process is highly automated and designed to handle the massive volume of cherry Coca-Cola produced daily while maintaining efficiency, accuracy, and product integrity. The first step in packaging is grouping the bottles and cans into multi-packs. Depending on the market and retail preferences, cherry Coca-Cola is sold in a variety of formats, including single cans, 6-packs, 12-packs, and larger 24-pack cases. The process begins with an automated system that arranges the bottles or cans into the correct configuration for packaging. High-speed robotic arms carefully align the containers into precise rows, ensuring uniformity before wrapping or boxing. These systems are programmed to adjust the layout based on production requirements, allowing flexibility in the types of multi-packs produced. For aluminum cans, a shrink wrapping system is used to bundle them together into multi-packs. The cans pass through a conveyor where they are tightly wrapped in a thin but durable layer of plastic film. This film is then heated in a specialized tunnel, shrinking it around the cans to create a secure and tamper-proof bundle. This method provides stability during transportation while allowing consumers to easily separate individual cans when needed. In some cases, paperboard carriers are used instead of plastic shrink wrap, particularly in regions where sustainability initiatives encourage the reduction of plastic packaging. These carriers are die-cut to hold the cans securely while allowing easy removal. For plastic bottles, the process differs slightly. Many multi-packs of plastic bottles are held together using plastic rings or shrink-wrapped trays. Larger cases of cherry Coca-Cola bottles are placed into corrugated cardboard boxes for additional protection. The use of recyclable materials is prioritized wherever possible to reduce environmental impact. Coca-Cola has implemented sustainable packaging solutions such as biodegradable plant-based plastics and recyclable wrapping materials to minimize waste. Some factories have also introduced lighter weight PET bottles that require less plastic while maintaining the same durability, further contributing to environmental goals. Once the cherry Coca-Cola bottles and cans are securely packed, they move to the palletization stage. A palletizer is a large automated machine that carefully stacks the packaged products onto wooden or plastic pallets in an optimized arrangement for stability. This process ensures that products do not shift or fall during transport. Each pallet is carefully configured to maximize space while maintaining structural integrity. The palletizer is programmed to create stable layers of product, with each row strategically positioned to distribute weight evenly. After the pallets are loaded, they are wrapped with industrial-strength plastic film to keep them secure. This stretch wrapping process ensures that the products remain stable during transport. In some cases, pallets are reinforced with corner protectors for additional stability, particularly when shipping long distances. Some facilities also use robotic pallet wrappers, which automatically detect the height and dimensions of each pallet to apply the precise amount of stretch film required for stability without excessive material use. Once wrapped, the pallets are labeled with tracking codes and barcodes that contain critical shipment information, including the product type, batch number, expiration date, and destination details. These labels ensure that the inventory can be accurately tracked throughout the supply chain, reducing the risk of misdelivery or loss. The tracking system also allows retailers to quickly verify shipments upon arrival and enables Coca-Cola to monitor stock movement and demand trends. The next step is warehouse storage and inventory management. Once the cherry Coca-Cola pallets are prepared, they are transported via forklifts to massive storage warehouses. These warehouses are temperature controlled to protect the beverage from excessive heat or humidity, which could affect carbonation levels or packaging integrity. Temperature regulation is especially important in regions with extreme climates, as fluctuations in temperature could cause the CO2 in the beverage to expand or contract, potentially leading to leaks or compromised carbonation. Advanced inventory management systems track every pallet, using barcodes and RFID technology to ensure efficient organization and retrieval. These systems automatically log incoming and outgoing shipments, allowing real-time monitoring of stock levels. Warehouses are organized using automated retrieval systems that move pallets using robotic arms and conveyor systems, further increasing efficiency in high-volume distribution centers. Once the products are stored, the logistics and distribution phase ensures that cherry Coca-Cola reaches retailers and consumers as quickly as possible. The logistics team carefully plans delivery routes based on demand, ensuring that distribution centers and retail locations receive fresh stock on schedule. The distribution model varies depending on the region, with some locations utilizing central distribution hubs that serve multiple retailers, while others ship directly from production facilities to large supermarket chains and wholesalers. Trucks are loaded with pallets of cherry Coca-Cola according to a strict loading schedule, ensuring that the oldest inventory is shipped first to maintain freshness. The loading process is carefully coordinated to optimize space while keeping products stable during transit. Many of these trucks are refrigerated or climate controlled, particularly in warmer regions, to prevent heat exposure that could compromise product quality. In some cases, insulated truck liners are used instead of full refrigeration, allowing for temperature control without the added energy cost of refrigerated transport. The process of making Pepsi begins with one of its most essential components, water. Water forms the majority of the final beverage, making its purification and preparation one of the most critical steps in the manufacturing process. PepsiCo takes extreme care in sourcing and treating water to ensure the final product is free from impurities, contaminants, and off flavors. Without this careful preparation, the beverage could have inconsistencies in taste, appearance, and carbonation retention. The journey starts with sourcing water from natural springs, municipal supplies, or underground wells, depending on the bottling plant's location. However, regardless of its origin, this water must go through extensive treatment to meet PepsiCo's strict quality standards. The process begins with initial screening, where water passes through coarse filters that remove large particles such as dirt, sand, and debris. This is followed by sedimentation, a method that allows heavier impurities to settle at the bottom while the cleaner water moves forward in the process. Once the larger impurities are removed, the next step is carbon filtration. This step is crucial for removing chlorine, organic compounds, and any unwanted odors or tastes that could interfere with the Pepsi formula. Activated carbon filters contain a highly porous material that traps chemical impurities while allowing pure water to flow through. This process not only improves the taste of the water, but also enhances its ability to mix well with the other ingredients later in production. But up next is the reverse osmosis process, one of the most advanced purification techniques used in beverage manufacturing. Reverse osmosis involves forcing water through an ultra-fine membrane under high pressure, effectively removing even the tiniest dissolved particles, including salts, minerals, and microscopic contaminants. This ensures that the water is as pure as possible before it becomes part of the Pepsi formula. To further refine the water, it undergoes ultraviolet sterilization. This step is essential for eliminating any remaining bacteria, viruses, or other microorganisms that could compromise the safety and shelf life of the beverage. High-intensity UV light disrupts the DNA of these microorganisms, rendering them inactive without the use of chemical disinfectants. Finally, before the purified water is stored, it goes through an ozonation process. Ozone, a highly reactive form of oxygen, is injected into the water to act as a natural sanitizer. This step ensures that the water remains free from microbial contamination while it is held in large stainless steel storage tanks, awaiting the next phase of production. Now that the water has been meticulously purified, it must be precisely balanced to create the ideal base for Pepsi. Even though reverse osmosis removes most dissolved solids, a controlled amount of specific minerals is added back into the water to optimize taste and improve its ability to retain carbonation. This step is carefully monitored as the mineral composition of the water can impact the final mouthfeel and texture of the beverage. With the water fully prepared and stored in sanitary tanks, it is now ready to be mixed with the other key ingredients that will give Pepsi its distinctive flavor. But before moving on to mixing, each batch of purified water is rigorously tested for quality. Samples are taken from the storage tanks and analyzed in PepsiCo's in-house laboratories. Scientists and quality control experts measure pH levels, mineral content, and overall purity, ensuring that each batch meets the company's global standards. If any irregularities are detected, the water is either reprocessed or discarded, preventing any inconsistencies from affecting the final product. Now that the water has been meticulously purified and stored in sanitized tanks, the next crucial step in the Pepsi manufacturing process is the preparation and addition of sweeteners. Sweeteners play a fundamental role in defining the flavor profile of Pepsi, contributing to its signature taste while also affecting mouthfeel, viscosity, and overall balance. The selection, processing, and precise blending of these sweeteners are critical to ensuring that every bottle and can of Pepsi maintains consistency across different production facilities worldwide. In most regions, Pepsi is sweetened with high fructose corn syrup, a liquid sweetener derived from cornstarch. However, in some markets, particularly in countries where cane sugar is more widely available or preferred, sucrose from sugarcane or sugar beets is used instead. Regardless of the source, the sweetener must be carefully refined and processed before being added to the beverage. The journey of high fructose corn syrup begins with corn milling, where harvested corn is cleaned, steeped, and ground into a slurry to separate the starch from the fiber, protein, and germ. The extracted starch is then subjected to enzymatic processing, where it is converted into glucose. A second enzyme is introduced to transform a portion of the glucose into fructose, increasing its sweetness. The result is a thick, viscous syrup that is then further refined, filtered, and tested to ensure the correct balance of glucose and fructose. The most commonly used variety in soft drinks is HFCS 55, which contains approximately 55% fructose and 45% glucose, closely mimicking the sweetness profile of cane sugar. For regions that use sucrose instead of HFCS, the sugar is derived from either sugarcane or sugar beets. Sugarcane is harvested, crushed to extract juice, and then boiled to concentrate the sugar, forming crystallized sucrose. Sugar beets, on the other hand, are sliced and soaked in hot water to extract sugar, which is then purified and crystallized. In both cases, the raw sugar undergoes extensive refining to remove impurities and ensure a uniform, pure sweetener. Once the sweetener is ready, it must be dissolved into a concentrated syrup before being mixed with other ingredients. In a dedicated mixing tank, the high fructose corn syrup, or dissolved sucrose, is blended with purified water in precise proportions to create a uniform, sweetening solution. This syrup is continuously agitated to prevent crystallization and ensure a consistent texture. To maintain Pepsi's exact sweetness level, refractometers are used to measure the syrup's sugar concentration, ensuring it falls within the specified range. At this stage, the syrup is also subjected to rigorous quality control testing. Laboratory technicians take samples from each batch and analyze them for purity, consistency, and microbial safety. Any inconsistencies in sweetness or viscosity could alter the taste of the final product, so adjustments are made, if necessary, before moving on to the next step. Now that the sweetener has been perfectly prepared, it is time to introduce the key flavoring components that define Pepsi's distinctive taste. Pepsi's flavor is the result of a complex blend of natural and artificial flavorings, including citrus oils, spice extracts, and caramel notes. The exact recipe remains a closely guarded secret, known only to a select few within the company, but it is widely understood that ingredients like orange oil, lemon oil, vanilla, cinnamon, nutmeg, and cola nut extract contribute to the drink's signature profile. The flavoring components are carefully blended into a concentrated mixture known as the flavor base. This highly concentrated liquid is prepared in a separate, sterile mixing tank, where precise measurements of each ingredient are combined under controlled conditions. Some of these ingredients, particularly the essential oils, must be emulsified using stabilizers to ensure they mix properly with the water-based formula of Pepsi. Without proper emulsification, the oils could separate from the rest of the beverage, leading to inconsistent flavor distribution. Phosphoric acid is then added to the flavor base, providing Pepsi with its signature sharpness and tangy aftertaste. This acid also plays a crucial role in preserving the beverage by inhibiting microbial growth. The level of acidity is carefully controlled to balance the sweetness of the drink and enhance its overall flavor. Caramel color, which gives Pepsi its deep brown hue, is another essential ingredient added at this stage. This colorant is created by heating sugar compounds under controlled conditions, resulting in a stable and safe coloring agent. The intensity of the caramel color is strictly regulated to ensure that every bottle of Pepsi has the same visual appeal. Once the flavor base is complete, it must be thoroughly mixed with the sweetener solution to create the final syrup that will be used in the soft drink. This blending process takes place in large stainless steel tanks, where high-powered mixers ensure even distribution of all ingredients. The proportion of sweetener to flavor base is precisely measured, as even a slight deviation could alter the taste of the final product. Before the syrup is approved for use, samples are taken and analyzed in a quality control lab. Tests include pH measurement, viscosity checks, and sensory evaluations, where trained tasters confirm that the syrup matches Pepsi's standard flavor profile. These rigorous quality checks ensure that every batch of syrup is identical, maintaining Pepsi's global consistency. Once the syrup has passed all quality control tests, it is stored in temperature-controlled holding tanks, ready to be mixed with carbonated water. These tanks are kept under strict sanitary conditions to prevent contamination and preserve the integrity of the syrup. But up next is one of the most critical aspects of the Pepsi production process: carbonation. This step is responsible for the effervescence and refreshing sensation that consumers associate with soft drinks. Without proper carbonation, Pepsi would lose its signature fizz, altering the drinking experience. The process of infusing the beverage with carbon dioxide is both a science and an art, requiring precise control over temperature, pressure, and gas concentration. To begin the carbonation process, purified water is first chilled to near freezing temperatures. The reason for this is that carbon dioxide dissolves more efficiently in cold water than in warm water, ensuring maximum carbonation retention. The chilled water is then injected with high purity CO2 gas under controlled pressure, creating carbonated water. This water is then carefully blended with the pre-mixed syrup in an exact ratio, typically around 5 parts carbonated water to 1 part syrup. The precise proportion ensures the correct balance of flavor, sweetness, and fizziness in the final beverage. Maintaining the right level of carbonation is crucial, as it directly affects the mouthfeel and shelf life of the product. If the carbonation is too low, the drink will taste flat and less refreshing. If it is too high, the beverage may be overly acidic or cause excessive foaming during packaging. To ensure consistency, carbonation levels are continuously monitored using pressure sensors and dissolved CO2 analyzers. The newly carbonated Pepsi must now be handled carefully to prevent the loss of carbonation before packaging. At this stage, the beverage is kept under constant pressure in specialized holding tanks to maintain CO2 solubility. Any sudden release of pressure could cause the carbon dioxide to escape, resulting in a less fizzy drink. With the Pepsi now fully mixed, carbonated, and held under precise pressure conditions, the next step is bottling and packaging. This is one of the most intricate parts of the manufacturing process, requiring extreme precision, speed, and cleanliness to ensure that every bottle and can of Pepsi is filled, sealed, and prepared for distribution without losing carbonation or quality. The bottling process must take place in a sterile environment to prevent contamination, and the machinery involved operates at incredibly high speeds to keep up with global demand. The first part of this process involves the preparation of bottles and cans. Pepsi is available in a wide range of packaging formats, including glass bottles, aluminum cans, and plastic bottles made from polyethylene terephthalate. Each type of container has its own preparation requirements, but all must be thoroughly cleaned and sterilized before being filled. For plastic bottles, the process begins with small, preformed PET molds called preforms. These preforms are heated to a specific temperature and then rapidly inflated using high-pressure air inside a blow molding machine. This machine expands the preforms into their final bottle shape, ensuring uniform thickness and durability. The freshly molded bottles are then conveyed into a high-speed rinsing station, where they are thoroughly washed with filtered water and food-safe sanitizing agents to remove any potential contaminants. Glass bottles undergo a more rigorous cleaning process since they are often reused. They are first soaked in a high-temperature caustic solution to break down any residue from previous use, followed by multiple rinses with clean, filtered water. Finally, they pass through a steam sterilization chamber to ensure that no microorganisms remain. Aluminum cans, on the other hand, arrive at the bottling plant pre-formed and ready to be filled. However, before filling, they are sent through a high-pressure air jet cleaning system that blasts away dust and debris. Since aluminum cans are highly sensitive to corrosion, a thin food-safe lining is applied inside each can to prevent any reaction between the beverage and the metal. Now that the bottles and cans are fully prepared, the filling process can begin. The carbonated Pepsi is transported through a network of pressurized stainless steel pipes that maintain the beverage's optimal CO2 concentration and temperature. The filling machines operate at high speeds, capable of processing thousands of containers per minute. For PET and glass bottles, filling is done using gravity-based or counter-pressure filling systems. In a counter-pressure system, the bottle is first pressurized with CO2 before the Pepsi is introduced. This prevents foaming and excessive carbonation loss during filling. The precise amount of liquid is dispensed into each bottle, with sensors ensuring that no underfilled or overfilled bottles proceed down the production line. Aluminum cans require a slightly different approach. Since they are more prone to CO2 loss due to their wide openings, the filling nozzles are designed to minimize turbulence as the liquid enters. The cans are quickly filled and then topped with a small injection of nitrogen gas to prevent oxidation before being sealed. Now that the containers are filled with carbonated Pepsi, the next critical step is sealing. This process must be done immediately after filling to prevent carbonation loss and contamination. For plastic and glass bottles, this involves capping. Screw-on plastic caps are applied to PET bottles using high-speed rotary capping machines, which tighten each cap with precise torque to ensure a secure seal. Glass bottles, often used for premium or international markets, are sealed with either metal crown caps or twist-off caps, depending on the region. Aluminum cans are sealed using a double seaming process. A lid, which contains an integrated pull tab, is placed on top of the can and then mechanically crimped around the rim. This creates an airtight seal that locks in carbonation and prevents leakage. With all the containers now sealed, they move on to the quality control phase. At this stage, random samples are pulled from the production line and tested for multiple factors, including fill level, carbonation retention, pressure stability, and contamination. Advanced X-ray and laser scanning systems inspect each bottle and can to ensure that there are no foreign particles, dents, or defects in the packaging. Any defective units are immediately rejected and removed from the batch. Once the beverages pass quality control, the containers proceed to labeling. Each bottle and can receives a label that includes branding, nutritional information, ingredient lists, and regulatory compliance markings. PET bottles have labels applied using heat shrink or pressure-sensitive label machines, while aluminum cans typically have their designs pre-printed onto the metal surface. After labeling, the bottles and cans are grouped into multi-packs for retail distribution. This process involves bundling them into various configurations, such as 6-packs, 12-packs, or full cases. Plastic shrink wrap, cardboard trays, or molded carrying handles are used to secure the multi-packs for easy transportation. The completed packs are then stacked onto pallets in an organized manner and wrapped in stretch film to stabilize them for shipping. Now it's time for one of the most logistically challenging aspects of Pepsi production: distribution. The pallets of finished Pepsi products are moved to temperature-controlled warehouses where they are stored before being shipped to retailers, grocery stores, vending machines, and restaurants. Since Pepsi is produced in enormous quantities to meet global demand, distribution logistics must be precisely managed to ensure that every store and vendor receives fresh products. Pepsi's supply chain is a highly coordinated operation involving fleet management, refrigerated storage, and just-in-time delivery systems. Large distribution centers act as hubs where shipments are sorted based on region and customer demand. Trucks, rail transport, and even cargo ships are used to move massive volumes of Pepsi across countries and continents. Once the products arrive at their final destinations, they are placed in cold storage or directly onto store shelves. In grocery stores and supermarkets, Pepsi is often stored in temperature-controlled sections to maintain freshness. Restaurants and fast food chains receive large volumes of Pepsi in bulk containers, which are connected to soda fountains for on-demand dispensing. Throughout this entire process, PepsiCo maintains strict inventory tracking and quality assurance programs. Each batch of Pepsi is assigned a unique tracking code, allowing the company to trace products back to their production date, location, and ingredient sources. This ensures that in the event of a recall or quality issue, affected products can be quickly identified and removed from circulation. With the Pepsi bottles and cans now filled, sealed, labeled, and packed for distribution, one of the final but most crucial aspects of the manufacturing process is ensuring product consistency, longevity, and consumer satisfaction. Maintaining Pepsi's signature taste and quality across millions of bottles and cans requires an advanced system of quality control, storage optimization, and packaging innovation. Every aspect, from the shelf life of the product to the materials used in packaging, plays a role in ensuring that each Pepsi delivered to a consumer is as fresh and enjoyable as the last. The first key factor in Pepsi's shelf life and consistency is its ability to retain carbonation over time. Carbonation, which gives Pepsi its signature fizziness, is created by dissolving carbon dioxide into the liquid under high pressure. The challenge is ensuring that this CO2 remains trapped within the beverage from the moment it is bottled until it is opened by the consumer. To maintain carbonation, Pepsi uses specially designed bottles and cans that act as airtight barriers, preventing CO2 from escaping. Plastic bottles made from polyethylene terephthalate are engineered with multiple layers that slow down gas diffusion, preventing CO2 from seeping out over time. The thickness and structure of PET bottles are carefully optimized to balance durability with weight, ensuring that the bottles are strong enough to retain carbonation while remaining lightweight for transportation. Aluminum cans provide an even better barrier against gas loss. Their completely sealed structure ensures that no CO2 escapes, preserving the drink's fizziness for extended periods. Additionally, a protective food-grade lining inside each can prevent any reaction between the metal and the beverage, which could otherwise affect flavor. Glass bottles, often used for premium markets or limited edition versions of Pepsi, offer the best gas retention of all packaging types. Glass is completely impermeable, meaning that Pepsi stored in glass bottles maintains its carbonation for the longest period. However, glass is heavier and more fragile than plastic or aluminum, making it less practical for mass production and distribution. Another critical factor in product longevity is preventing oxidation. Exposure to oxygen can alter the taste of Pepsi, causing it to become flat and develop off flavors over time. To counter this, PepsiCo employs nitrogen dosing in certain packaging lines. This process involves injecting a small amount of nitrogen gas into PET bottles just before sealing. The nitrogen displaces any residual oxygen inside the bottle, reducing the risk of oxidation while also adding structural rigidity to the bottle, preventing it from collapsing under vacuum pressure. Beyond carbonation and oxidation control, preservatives also play a role in maintaining Pepsi's freshness. While the beverage's acidity and carbonation naturally inhibit microbial growth, additional preservatives such as sodium benzoate are included to extend shelf life further. These preservatives prevent mold, yeast, and bacterial growth, ensuring that Pepsi remains safe for consumption for months or even years after production. Now that the beverage's stability is secured, it must be stored and transported under optimal conditions. Pepsi is highly sensitive to temperature fluctuations, which can affect carbonation retention and overall flavor. As a result, warehouses, distribution centers, and retail storage areas are kept within a controlled temperature range to prevent heat exposure. Excessive heat can accelerate CO2 loss in plastic bottles and increase oxidation reactions, leading to a flatter, less refreshing drink. To counteract this, refrigerated warehouses are used in regions where high temperatures could compromise product quality. During transportation, trucks equipped with climate control ensure that Pepsi is not exposed to extreme heat or direct sunlight, both of which could degrade the beverage. Another major factor that affects Pepsi's taste consistency is the impact of light exposure. Ultraviolet light can break down some of the organic compounds in Pepsi's flavoring, leading to unwanted taste changes. This is why Pepsi bottles, particularly those made from PET, are designed with tinted or opaque plastic to reduce UV penetration. Aluminum cans and glass bottles naturally provide complete light protection, further ensuring product stability. Once Pepsi reaches its final retail destinations, whether in grocery stores, vending machines, or fast food chains, it is crucial that storage guidelines continue to be followed. Retailers are instructed to keep Pepsi stock rotated, ensuring that older products are sold first and newer shipments are stored properly. This helps maintain product freshness for consumers while preventing expired stock from sitting on shelves. Fast food chains and restaurants that serve Pepsi from soda fountains have additional steps to ensure taste consistency. Instead of pre-packaged bottles and cans, Pepsi is delivered to these locations in large pressurized syrup containers known as bag-in-box systems. These containers hold concentrated Pepsi syrup, which is mixed with carbonated water on demand through specialized dispensing machines. The bag-in-box system allows for efficient storage and prevents waste, as restaurants can control the syrup-to-water ratio for optimal taste. These systems are regularly maintained, with filters and carbonation settings adjusted to match the ideal flavor profile. Additionally, PepsiCo provides restaurants with quality control tools to measure CO2 levels and syrup concentration, ensuring that every poured glass tastes as good as a bottled Pepsi. With all these measures in place, Pepsi is now fully ready for consumers to enjoy. But beyond the immediate production and distribution, PepsiCo continually invests in research and development to improve manufacturing efficiency, sustainability, and packaging innovations. One of the company's most significant focuses in recent years has been reducing the environmental impact of its packaging. PepsiCo has made major advancements in recyclable PET bottle technology, developing bottles that contain post-consumer recycled plastic to cut down on waste. Additionally, the company has experimented with plant-based PET alternatives that reduce reliance on petroleum-based plastics. Aluminum cans have also been a major target for sustainability improvements. Since aluminum is highly recyclable, PepsiCo has worked to increase the amount of recycled aluminum used in can production. The company encourages consumers to participate in recycling programs, ensuring that cans are properly collected and reused. In some markets, PepsiCo has even introduced refillable glass bottle programs, allowing consumers to return used bottles for sanitation and reuse, significantly cutting down on single-use waste. Further technological advancements in bottling machinery have also improved efficiency in the production process.